Welcome to this explainer. When you just casually look up into the night sky, it's pretty easy to just see a chaotic, random scattering of lights. But to an astronomer, clusters of stars are essentially perfect, dynamic laboratories for understanding exactly how the universe evolves. And today, we're focusing on one absolutely breathtaking cluster that has sparked a genuine cosmic detective story. We are unraveling Caldwell 58.
Now, long before modern astrophysics and digital telescopes, this cluster was actually spotted by the pioneer astronomer Caroline Herschel way back on February 26, 1783. And she described it so perfectly in her notes as a beautiful cluster of pretty compressed stars near 1/2 degree in diameter. But what's kind of crazy is that her brilliant observational notes were totally overlooked at first. It wasn't really until her brother, William, included the cluster in his 1786 catalog that it gained wider recognition. But, history remembers. And today it's affectionately known as Caroline's cluster.
Okay, so let's get our bearings here. Our main subject is Caldwell 58, Caroline's cluster. It is situated a staggering 3,000 light-years away from us, sitting squarely in the Canis Major constellation. To put that distance into perspective, the light we are seeing from it today literally started its journey through the cosmos around the time of the ancient Egyptians. And because it's an open star cluster, it's a group of stars formed from the exact same giant molecular cloud. That means they're all roughly the same age and have similar initial chemical makeups. Because of that shared origin, Caldwell 58 provides us with an absolutely brilliant baseline for figuring out how stars live, age, and eventually die.
Part 1. The Cosmic Fingerprint. So, to map out a star's life cycle and truly understand the history of Caldwell 58, astronomers can't just rely on a pretty photograph. They have to treat the cluster like a cosmic crime scene and look for its unique fingerprint.
And that fingerprint is what we call a color magnitude diagram, or a CMD. It's a completely essential tool in the astronomer's toolkit. By plotting a star's brightness on one axis and its color, which by the way corresponds directly to its temperature on the other, we can visualize the life cycle of an entire population of stars all at once. Most stars in their prime, the ones actively burning hydrogen, will form a really distinct, predictable curve on this graph that we call the main sequence.
When we actually map out the stars of Caldwell 58, the main thing we're hunting for is the main sequence turnoff. See that distinct hook-shaped bend in the data points? That is the exact, literal moment stars exhaust their core hydrogen fuel and veer off this main curve to become red giants. Finding that precise turnoff point is absolutely crucial.
Which brings us to part 2, determining the cluster's age. Pinpointing exactly where that hook happens on the graph acts as our cosmic clock. Massive, bright stars burn their fuel incredibly fast, so they turn off early. As the cluster ages, less massive stars begin to turn off. Sounds like a really straightforward way to tell time, right? Well, solving this isn't always quite that simple.
In fact, different scientific analyses of Caldwell 58 have yielded wildly different age estimates. Depending on the exact methodology used, studies have placed Caroline's cluster at 708 million years old on the younger end, all the way up to 1.4 billion years old on the older end. That is a massive discrepancy. A difference of roughly 700 million years means our supposedly perfect cosmic clock is actually pretty blurry.
So, why is it so hard to just pin down the age? Well, it's because these age models rely heavily on a super delicate balance of intertwined variables. You got to account for metallicity, which is just the star's chemical makeup, and interstellar reddening. Actually, interstellar reddening is really just a fancy way of saying there's a bunch of cosmic dust blocking our view and changing the apparent colors of the stars. Historically, adjusting all these variables to fit the theoretical curve was a subjective by-eye process. It's kind of like trying to guess someone's age while squinting through a dirty window. If you tweak your dust estimate even a tiny bit, the whole age estimate shifts dramatically.
Part 3. The Yellow Straggler Mystery. Okay, just when astronomers think they finally have a handle on the age of Caldwell 58, the cluster throws us a massive, fascinating curveball. As scientists meticulously cleaned up the data, they found anomalies. Peculiar stars that completely defied the standard evolutionary models.
Enter the yellow stragglers. These are rogue stars that occupy a forbidden zone in our cosmic fingerprint. In the standard model of a cluster's evolution, there's a region called the Hertzsprung gap, where typical red giants simply shouldn't be found. It's a transitional phase that stars pass through so rapidly that statistically we almost never catch them just hanging out there. And yet, there they are, totally defying the odds.
When we look closely at Caldwell 58's data, check out stars number 92 and 96.
marked here in red. They stick out like sore thumbs. They're sitting right in the middle of this Hertzsprung gap. Their colors have dramatically shifted, making them appear significantly bluer than the red giants they're supposed to be. Yet they are completely detached from the main sequence of younger stars.
So, the million-dollar question becomes, what on Earth is causing these two specific stars to masquerade as anomalies? Are our entire models of stellar evolution just fundamentally broken? Or is something else masking the true nature of stars 92 and 96?
Part 4. Binary Stars Unveiled. To figure out what these yellow stragglers really were, astronomers realized basic photography just wasn't going to cut it. They had to zoom all the way in using high-resolution optical spectroscopy. They needed to pull the light from these specific stars apart to see exactly what they were made of.
By breaking down the exact wavelengths of light emitted by these stars into a spectrum, we can search for really specific chemical signatures. You see, every element absorbs light at a very specific wavelength, leaving dark lines in the spectrum. It basically works like a literal barcode of the star's atmosphere, giving us its exact chemical makeup.
And when the spectroscopic data for stars 92 and 96 came back, the clues were shocking. The data showed severe veiling, meaning the typical features of a red giant star were literally being washed out by extra light. Their chemical signatures had bizarre, distorted shapes that a standard star just wouldn't produce on its own. Honestly, the spectrum looked like two completely different light sources mashed together into one blurry barcode.
And here is the grand resolution to our cosmic mystery. The plot twist. Stars 92 and 96, they aren't single stars at all. They're binary systems. What the spectroscopy proved is that these red giants have a hidden, much hotter A-type companion star orbiting right along with them. This hotter, bluer companion is shining brightly enough to distort the combined color of the system. And that is exactly what shifts their data points right into the Hertzsprung gap, making them appear as anomalous yellow stragglers.
It is such a brilliant reminder that in astronomy, things are rarely exactly as they appear at first glance. Knowing that Caldwell 58, Caroline's cluster, is actively hiding these complex binary systems within its ranks, it leaves us with a truly fascinating thought. If these companion stars were hiding right in plain sight, masquerading as single rogue stars, what other incredible cosmic secrets, unseen white dwarfs, or bizarre phenomena are just waiting to be discovered right now in the 3,000 light-year depths of Canis Major? Thanks for joining me for this explainer, and keep looking up.